Hello, students. We're going to review the organic chem introductory organic chem class exercise. So you notice that there's only one compared to your seniors. If you have seen what your seniors have, I think they have two. So what we did was that we streamlined a little bit, and that explained why there needs to be a new recording, because for the previous exercises, although there were some changes, but there isn't a need for a new recording to be done. But it's okay. So this particular streamlined version, I think it covers most of the things you need to know for introductory organic chem. Okay, so for question 1, you were told that you have this noradrenaline. It's a hormone released into the body when we become stressed. Question asks you to name 3 functional groups. So I'm going to highlight 3 functional groups. Okay, so these are functional groups other than phenol. Okay, so very explicitly they say, okay, you cannot name phenol as one of the functional group. So what exactly is phenol? Okay, so if you're aware, right, if I have C6H6, that is a 6-membered ring with a delocalized electron cloud. So each of the carbon will only be bonded to one H, because each of the carbon is sp2 hybridized. And this compound is known as benzene. Okay, Benzene. And when benzene is being substituted, so for example in our case here, so let's say it's being substituted with, let's say, CH3, then this ring is no longer called a benzene ring. So I know that sometimes you hear people talking about, oh, that benzene ring, this particular benzene ring, but the more accurate term is phenol, or sometimes people call it phenol. Okay, it's called a phenol ring. So I'm going to just highlight in yellow. So this is the phenol ring we're talking about. Okay, you can call it benzene ring if you wish, but it's not the most accurate term, just to let you know. Okay, so we call it the phenol ring. And phenol is not meant to be confused with phenol. Okay, so phenol is actually a functional group. So it contains a phenol ring, okay, and an OH like this. So this particular compound is known as phenol. Okay, so if you look at your introductory organic chem notes, you will learn about this. So yes, so one of the functional group is phenol, so I'm just going to write it out here. So this is phenol. Okay, you don't really say it has a phenol ring. This is not very accurate. So normally we say that a phenol contains a phenol ring. So that will be a more accurate representation. Sometimes if you wish to annotate the OHs that are bonded to the phenol ring, you don't really call them phenol OH. I mean, it's not a very accurate term. The more accurate term is actually called the phenolic OH. Okay, so that means that it is the hydroxyl group that is bonded to the phenol ring, and this hydroxyl group has the property of phenol, so we call them phenolic OH. Okay, then what about the rest of the functional group? Okay, so we probably want to expand this out to make it a little bit clearer. Okay, so I'm just going to extend this. I'm not going to draw the phenol ring out, so I'm just going to put a C with a H, and then with a OH here, and then a CH2. Okay, and then NH2. So I'm just going to put NH2. So you'll notice something interesting, because this is an OH bonded to an alkyl chain, right? So in particular, we call it an alcohol. But for the purpose of H2, and of course for making terminology, or we want to make the terminology very accurate, in particular, we call this alcohol a secondary alcohol. So you have to spell the word out: secondary alcohol. Okay, sorry, I mean this is not working very well. Alcohol. Okay, it's called secondary alcohol. If you want to know how to differentiate between primary, secondary, and tertiary, you might just want to look at the future set of notes. But in short, a secondary alcohol usually have two other groups bonded to the carbon. Okay, so I'm just going to circle it for you. So these two groups are this large group and then another large group here. Yeah. So if you have three other groups, we call that a tertiary alcohol. Yeah. So if there are only one of that group, we call it a primary alcohol. So I hope that is easy for you to remember. Yeah. And if you could also recall, this is known as an amine. Okay. So in particular, it's a primary amine. Okay. So we're just going to spell out a primary amines. Okay, yep. You might hear or you might have seen annotation like primary as 1 degree and then secondary as 2 degree. Yeah, but when we write it as 1 degree or 2 degree, we don't call that 1 degree or 2 degree. Okay, we still pronounce it as primary and secondary amine. Yep, it might be important for you to take note of this so that you don't sound weird when you tell people that this is called a 2 degree alcohol, but it's actually called a secondary alcohol. Okay, yeah, so perhaps you should not be too stressed over memorizing all the different functional groups. I think it's easiest if you just study them as you go. Yeah, so in JC1, you're going to learn about alkanes, and arenes. Yep, so until promos will be alkenes, but after promos you will learn about arenes. Then in JC2 you will learn the rest of the functional group. So just take your time, assimilate the knowledge as you go. Okay, so then next for question 2, we have this particular reaction scheme. It shows some reaction that compound A undergoes. Okay, so there are a series of reactions. So we're just going to go according to the numbering here, the Roman numerals, so 1 to 8. So basically you are supposed to state the types of reaction that occurs during each of the steps using the following terms. So substitution, addition, blah blah blah. Okay, so for the one depicted by 1, Br2 in CCl4 absence of UV, you notice that if you just pay attention to the highlight, you notice that the Br is being added across the CC double bond. That means that the pi bond is being broken. Nothing is being released. Okay, you notice that the H remains intact. So I'm just going to highlight the H. So there are 3 H's here. The H's here remain intact. Yeah, so this is typical of an addition reaction. Okay, so number 1 is an addition reaction. Okay, I won't bother to write it out. Okay, so I'll just narrate as I go so that it's actually easier for you. Or if you wish to, I can just write it out over here. So this is a typical of an addition reaction. Okay, if you look at number 2 or reaction 2, right? So I'm just going to also highlight the H's here. So the H's remain intact as well. Okay, so what happens here is that it seems that the OH it's kind of being added across the double bond. Yeah, but of course the mechanism doesn't happen that way. Okay, it happens through similar to an addition reaction, but not quite similar. Yeah, so at this stage, if you wish, you can call it an addition reaction. But normally, when oxygen is being added, we tend to call it an oxidation. Okay, so oxidation might be a better answer here, but if you call it an addition, I think that is fine as well at this stage. Okay, then for reaction 3, we have ethanolic sodium hydroxide. Okay, so what's going to happen here is, okay, so I'm just going to highlight again in red. You'll notice that the HCl is being removed. Okay, this HCl is being removed, and the remaining H's remain intact. Okay, so I'm just going to highlight them for you. Okay, so over here I'm just going to write minus HCl. Yeah, so this is very typical of what we call elimination. So basically you are eliminating HCl from compound A. Alright, then for reaction 4, the condition is hydrogen nickel high pressure. Yeah, so this might be something familiar from what you have learned in secondary school. Is what we call catalytic reduction. Okay, so that means that the CC double bond, the pi bond, you have H being added across it. Yeah, through a mechanism not really called addition, but again in this case you can call addition if you want, because what exactly is happening is that the CC pi system interacts via some form of dispersion forces or some weak interaction with the surface of the metal, and then in the process the pi bond gets weakened, and then the hydrogen radical that is being so-called distributed across the surface due to the presence of the metal and hydrogen gas, the hydrogen can then be added across the two carbon. Okay, so if I'm going to highlight, it will look the same. So this will be the original. Oh, sorry, I should use the same color. So this is the original one. Okay, and then the one that is added across it will be this and this. Okay, yeah. So this reaction, you can call it catalytic reduction. So I'm just going to write it out. Catalytic reduction. Okay, or you can simply call it an addition reaction. Okay, yeah. Then what about for reaction 5? Okay, so for reaction 5, right? Okay, I'm just going to remove the highlights so that it's easier. Okay, just going to focus on this part. You'll notice that for reaction 5, the Cl is being replaced by OH. Yeah, so it's a replacement. So replacement reaction in chemistry, we call it substitution. Yeah, so you can say that the Cl is being substituted for the OH. Yeah, so this is a form of, later on you're going to learn, it's called nucleophilic substitution, because your OH minus is behaving as a nucleophile. But again, you shouldn't be too stressed with all these terminologies. Then for reaction 6, yeah, you'll notice, let us look at some pattern recognition. Okay, so again, I'm just going to erase this, zoom in a little bit, highlights. Okay, just going to highlight two portions. I'm going to highlight the H and the Cl. Okay, and then I'm going to just highlight the molecule over here. So this OCCH3. Okay, this OCCH3 is here. Yeah, so what do you notice? You notice that the reaction actually happens between this particular functional group known as an acyl chloride and the primary alcohol, and then in the process HCl is being released. Yeah, so it's like two combined to give one molecule with the release of a small molecule. Yeah, this kind of reaction you have met them before in secondary school. It is called a condensation reaction. Yeah, two combine into one, and then in the process it drives out a small molecule. Okay, so there's an option here, condensation. Yeah, so this is an example of a condensation reaction. Then for number 7, you notice that the ester, so this new functional group, I'm just going to erase this for now. Okay, so this new functional group, COO, yep, this is called an ester functional group, or we call it ester linkage. Yep, and then what's going to happen is that it is subjected to this particular condition with acid. Yeah, so of course in this case acid act as a catalyst. Yeah, so the one that is involved in the reaction is actually water. But again, H2SO4 or the acid itself acts as a catalyst. So you can view it that after the reaction, okay, I'm just going to draw out the water molecule more nicely. Okay, so water is like this, like this. Okay, so I'm just going to highlight the water molecule in pink. Okay, this is the H. Yep, so you notice that the H can be found here and the OH can be found here. Yeah, so in this particular reaction, water assists in breaking up the ester. Yeah, so this kind of reaction is known as hydrolysis. Hydro means it involves water. Lysis means it involves the breaking of some bonds. In this case, it's the breaking of the ester linkage. So in particular, this is the bond that is broken. Okay, so I won't go into further details because you do not need to know the mechanism of the reactions. And if you want to know the detailed mechanism, you can learn that either on your own, or you can consider taking up a H3 course next year. Okay, next we're going to discuss question 3. So for question 3, we are practicing what we call drawing or be comfortable with the drawing of arrows. Yeah, because we are required to represent the movement of electron using curly arrows. Yeah, so again, let us just recap. The curly arrows begins with what we call an electron source. Okay, which can be lone pair or pi bonds. Okay, so electron source. And then it's pointing towards what we call an electron sink or electron deficient sites. Okay, the electron deficient sites can be maybe unsaturated, so it doesn't have the octet configuration. So maybe I just put an inverted comma, no octet configuration. Okay, or it tend to have, say, a plus charge. Okay, so this no octet configuration means that it will either have a plus charge or it could be neutral as well. Okay, so later on we will see. Right, so it doesn't mean that the electron source must attack a plus, because sometimes the site with a plus charge, it could be already saturated. Okay, yeah, but anyway, you learn as you go, so let's not go too much into unnecessary details. Okay, so for 3A, what's going to happen is that this lone pair of electrons is going to attack the H. Okay, actually, sometimes students ask, how do you know? Okay, you know it because you notice that the OH sigma bond is being formed, and therefore the lone pair must attack the H, or must be donated to the H, and the donation of this lone pair will result in the heterolytic cleavage of the HC bond. And now, if you take a look at this, right, the cleavage result in the lone pair of electrons being generated. Okay, so I think highlighting might be better. So this is the lone pair being generated, and then now the carbon takes on a negative charge. Okay, so basically, if you look at a dot and cross diagram, it's like this, with a dot here, and then carbon, then dot, 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 cross, cross, cross with an N. Okay, so now what's happening is that you can envision it as this H is being so-called donated to the alcohol, to the oxides, or to the O with a minus charge, and then this original sigma bond is now part of the CN system. And because originally carbon has only 4 electrons, yeah, so now it has one excess that comes from the H, so it takes on a -1 charge. Okay, so that's how we can deal with the situation why it has a -1 charge. Another way you can look at it is based on the conservation of charge. Meaning that the total charge on the left is -1, so the total charge on the right must also be -1. Okay, yeah. Then for B, it will be the same story. So we notice that a new CH bond is being formed. Okay, so I'm just going to highlight. So this is the new CH bond being formed. Yeah, so it's formed between this C and this carbon. Okay, so you can envision it as the pi bond attacking the H, and then this result in a heterolytic cleavage of the HBr. Yeah, and then similar to the HCN idea, now the Br will gain a lone pair. Okay, so originally it already has 3 lone pairs, so now it gains 1. Yeah, so this is the lone pair being gained, and that's why it takes on a negative charge. Okay, and the particular carbon here has only 6 electrons. Yeah, so it's 1 electron short, and that is why it contains the +1 charge. Yep. So if you wish, maybe I can just do a little bit of illustration here, because this portion tends to be a little bit confusing with students. So I'm just going to just pardon me. I just need to erase this portion so that I can draw the dot and cross diagram out for the C double bond, the alkene, and then it makes it a little bit clearer. Okay, so your original alkene is like this with a carbon. Okay, like this, and then cross cross, dots dots, carbon, and then dots cross. Okay, so I won't expand the CH3. Okay, so pardon me for my half big dot and cross diagram, but as long as I can illustrate the point, I think that's good enough. Okay, my apologies once again. Right, so now the 2 carbon, sp2 hybridized carbon, has an octet configuration, so we are very clear about that. And then what's happening is that in the process of electrophilic addition, I'll just narrate and erase as I go, so it's easier. Yeah, one of the pi bond, or actually just the pi bond, right, donates to the H. Okay, so I'm highlighting the two bonds, or rather the bond, or the the 2 electrons that are donated to the H. Okay, so once that happens, okay, I'm going to use my eraser. I'm just going to erase this. Okay, so this is donated, and then I'm just going to put in red. Okay, so like this to the H, right? Like this. Okay, then what's going to happen is that originally they don't have a charge, right? As you can see. Now this carbon, if you count, it has 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. So that it shouldn't have a charge. But this carbon now is 1 electron short. Yeah, because the bond breaks heterolytically. It's not homolytically. Yeah. And you notice that the original electrons, which belongs to to the carbon, right, reduces from 4 to 3. Yeah, because one of it is being used to donate to the H, right? So now it takes on a plus charge. And it's a carbocation because it's electron deficient. It contains only 6 electrons around it. In terms of hybridization state, it is sp2 hybridized with a empty p orbital. Yeah, and because of that, later on you're going to learn this reaction known as electrophilic addition, because now the carbocation center is susceptible to attack by the bromides. So the bromide is over here. Okay, yeah, so I hope using dot and cross diagram helps you to understand the picture a little bit better. But as you learned, I mean, along the way, there isn't a need for you to use the dot and cross diagram to help you understand this idea, right? Okay, then the next thing is we have this radical. Okay, this radical over here. Then what's going to happen is that there's a new bond being formed over here, this Cl. Okay, so I expect this C and this carbon to form a bond. Yeah, so in this case, I expect a homolytic cleavage. Yeah, so this bond will break homolytically. Okay, so one of it goes to the Cl. So this Cl originally has 7 electrons. Now it has 7 electrons back. Okay, that's why it doesn't have a charge. Okay, so the lone pair is originally here. Okay, like this. Yep. And then after that, that's why your Cl has no charge. And then this Cl, the radical used to combine with this particular radical from the carbon, and then eventually it forms a CCl sigma bond. Yeah. And if you look at the left, there's no charge. You look at the right, there's also no charge. Okay, so because of that, then no charge. So radical has no charge. Yeah, one of the common misconceptions students have is that there's charges to the radicals, but that is not the case. Okay, yep. Gonna move on to question 4. Okay, so for question 4, you were told you have 3 compounds, X, Y, and Z. I don't think I need you to know the function group, but if you wish to know, they contain what we call the carbonyl group. Okay, so this is called the carbonyl group, C double bond O. Okay, the carbonyl group has a very important characteristic. Okay, electron density is withdrawn towards the oxygen. So because of that, it makes the oxygen take on a permanent negative charge. It makes the carbon takes on a permanent positive charge. Okay, delta minus here, and then delta plus. Okay, then because of that, the carbonyl carbon is what we call electron deficient. So therefore, it is an electrophilic site. Yeah, this is a pretty important term, or you can just say that it is the carbonyl carbon is electron deficient. Okay, because electron density is being displaced towards the oxygen. Okay, so towards the oxygen. Okay, due to electronegativity difference between the two. Okay, or you can say due to the fact that oxygen is more electronegative than carbon. Yeah, this is not exactly to answer the question. Can I just qualify it? Okay, the answer to the question I have narrated along the way, but I thought I just want to highlight to you some of the ways you can talk about the carbonyl carbon. Yeah, just need to highlight that it's electron deficient, and because oxygen is more electronegative than carbon, so electron density is displaced towards the oxygen, and that makes the carbonyl carbons highly electron deficient and highly susceptible to nucleophilic attack. And then you were told to complete the mechanism of the following step by drawing all relevant curly arrows. Okay, so the cyanide, the lone pair, you can draw it. So you will attack this carbon. Okay, how do you know that it will attack this carbon? You know it because there is a new bond being formed over here. Let me just highlight. Yeah, there's a new bond being formed here. So because there's a new bond being born over there, being formed over there, that means that the electron density of the carbon in cyanide must attack the carbonyl carbon. And you notice that the oxygen gains a negative charge. So therefore, the pi bond must be broken towards the oxygen. So we put a delta minus here and a delta plus here. Okay, so this is the typical example where for very beginning students, right, we say that electron density flows from the electron source all the way to the electron sink. Yeah, so it always goes from the source to the sink. So it goes in one fashion. So source to sink, source to sink, source to sink, like this. Okay, yep. And then for C, with reference to B, explain why cyanide can act as a nucleophile. What is the focus here? The focus is that it is electron rich at the carbon. Yeah, because the carbon bearing the negative charge has a lone pair of electrons. Okay, and then explain the effect of changing H in Y to CH3 in X on the electron deficiency of the carbonyl carbon. Hence, explain why X is less reactive than Y towards nucleophile in terms of electronic effects. This is very important because the highlight here is in terms of electronic effects. Okay, now we need to compare between X and Y. And then you notice that for X, there are two CH3 over there. And then for Y, instead of the CH3, now I have the H's. Yeah, so what is the difference in the reactivity and why such difference exists? You will notice from the lecture notes and some of the exercises you have in the lecture notes, yeah, that CH3 group or LQ group in general, they are what we call electron donating groups. That means that the LQ groups will donate parts of their electron densities towards a particular center they are directly bonded to. So that means that, let me zoom in, that means that for this particular CH3, which maybe I'm going to highlight in maybe in yellow, the CH3, right? The electron density will be donated towards the carbonyl carbon. Yeah, so the donation of electron density, right, will sort of partially mitigate the displacement of electron density towards the carbonyl oxygen. Yeah, so that means that it will make the carbonyl carbon, or it will make this particular carbon less electron deficient than it would be without the CH3. That means for Y, without the CH3, the carbonyl carbon will be more electron deficient as compared to that of X. Okay, so I hope that is so-called clear enough. So that is why X is less reactive, or rather, sorry, okay, so X is less reactive as compared to Y. Yeah, because the carbonyl carbon in Y is bonded to two H's over here. Yeah, but compared to X, they are replaced by CH3, and CH3 being electron donating will make the carbonyl carbon in X less electron deficient than that in Y. Yeah, so because of that, the carbonyl carbon in Y will attract nucleophile more readily. Yeah, so that is based on electronic effects. Yeah, so in general, there are two effects we need to understand in chemistry. So I'm just going to write it out. It's either electronic or what we call steric. So if it's not electronic effect, it will be steric effect. Yeah, then I think part E asks you to explain in terms of steric effects. Yeah, I think in terms of steric effect, that's usually the favorite of students because they just look at the size. So you notice that the CH3 is larger in size as compared to H. Yeah, so being larger in size, it will be able to repel the incoming nucleophile via what we call steric hindrance. Yeah, so the CH3 being bigger size than H will repel the incoming nucleophile. Yeah, so that makes the incoming nucleophile more difficult to approach the carbonyl carbon. Yeah, so because of that, it is likely to have a larger activation barrier. So therefore, because if the temperature is not high enough, it will react more slowly as compared to Y. Okay, yeah, so that is the difference in the explanation between electronic and steric effect. So electronic effect has got to do with how the nature of the groups bonded to the center, right? How it affects it. Is it going to donate electron density towards it? or is it going to withdraw electron density away from it? And then steric has got to do with the groups, the bulkiness of the group that surrounds that particular center we are interested in. Yeah, is it going to repel the incoming nucleophile or electrophile, or is it going to make it easier for the incoming nucleophile or electrophile to approach? Right. Then finally we have F. There is delocalization of electrons in Z that makes the CO carbon, the carbonyl carbon, less electron deficient. So on the diagram of Z above, sketch the arrangement of p orbitals involved in the delocalization, and hence explain why the CO, the carbonyl carbon in Z is less reactive towards nucleophile. Okay, so you can either sketch here, or I can just use the space below. Okay, so a simple sketch will do. So I'm just going to sketch like this: carbon, 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 O. Okay, so the p orbitals, they form a continuous overlap. Okay, like this. Okay, I'm just going to, for oxygen, I'm going to put in red. Yeah. Okay, so there is this continuous overlap of electrons in the pi electron clouds. Yeah, but of course, if you heard me during tutorials, because the CC bond is freely rotatable, yeah, so this delocalization happen only when all the p orbitals are aligned. Yeah, but needless to say, right, this will represent one of its most stable states, because allowing the pi electron cloud to be delocalized in this manner reduces its electronic energy by quite a bit. So because of that, this is one of the conformation that it prefers. So meaning like this, and then having all the p orbitals aligned in this particular fashion. Yeah, and because of the delocalization of electrons from the CC pi bond, right, it makes the carbonyl carbon less electron deficient. Yeah, so that means that this carbonyl carbon is actually less electron deficient as compared to that in, say, Y. Yeah, so because of that, it is less susceptible to nucleophilic attack, or you can say that it is less able to attract the incoming nucleophile. Okay, yeah, so I hope that this review helps you perhaps to understand a little bit more about some of the terminology, how to use some of the terminologies. Of course, it's the first time that most of you have heard of all these terminology, so it will be very useful if you review the notes again, like introductory organic chem, and then as you learn organic chemistry along the way, remember to think about reactivity in terms of electronic and steric effect. I think that will help you a lot in the coming months, so that you can appreciate organic chem as a sub-discipline of chemistry.